Hey guys, what's up and welcome back to the Rocket Hub. My name is Philip and today we're going to dive into a very underestimated aspect of space travel. But underestimated doesn't mean unimportant. In fact, we will be talking about engineering challenges which are essential for human spaceflight. To make this video a bit more accessible for you, I have divided it into different chapters with timestamps on screen right now. The YouTube playbar is also broken up into these chapters. What do a plane struggling to remain airborne, the mutations in your genetic code, and a starship on the way to Mars have in common? At first, this question seems a bit ridiculous, and these three examples appear to have nothing in common at all, especially the one with the DNA, since that isn't even technology. But those of you who have heard about this problem before, or those of you who have read the video title, may already know what I'm talking about. Today, we will be talking about galactic cosmic rays. All of the three examples given are negatively influenced by the results of being bombarded with cosmic rays. But why exactly are cosmic rays a problem for spacecraft and their passengers? And what can we do to protect ourselves from cosmic rays? Those questions are pretty important and we are going to answer them over the course of this video. But at first, we have to go through the very basics of the topic. So, what are cosmic rays and what are they capable of? Cosmic rays are a very special form of radiation. In fact, cosmic rays aren't even one type of radiation, but consist of anything from single electrons to entire atomic nuclei and even some antimatter particles. The only reason for accumulating all these types of radiation into one group is the fact that they are reaching us from deep space, therefore the alternative name, galactic cosmic rays. Our knowledge of cosmic radiation began in the early 20th century, after Henry Becquerel had discovered radiation in general back in 1896. Early electrometers were used to measure the rate at which the radiation produced different ions. And those electrometers showed that radiation was everywhere, and scientists concluded that all of the radiation must come from radioactive atoms in the soil below our feet. By 1912, this theory was widely accepted among scientists, although there was some confusion generated by weird measurements conducted underwater showing rather unexpectedly low values. But in 1912, an Austrian scientist with the name of Victor Hess took a few electrometers high up into the sky on a hot air balloon. Contradictory to what the publicly accepted theory was, his electrometers showed dramatically increased values the higher he went. This discovery confused pretty much anyone back then, since it indicated that our knowledge about the source of radiation was all wrong. Hess even conducted such a flight during a total solar eclipse and measured the same values, so he could rule out the sun as a potential source of the rays he found. For him, it was clear that the phenomenon he had discovered originated from outer space. In the early to mid-20th century, the research on cosmic rays ramped up dramatically and scientists figured out the exact composition of particles. But for a very long time, we didn't know where cosmic rays even came from. It took us years to prove that high-energy cosmic rays mostly originate from supernovae and black holes. Therefore, the secondary name, galactic cosmic rays. Cosmic rays consist of primary and secondary rays. Particles known as primary rays directly originate from the emitting sources somewhere in the universe, even galaxies millions of light years away. Those particles move incredibly fast, and some of them, like the OMG particle recorded in 1991, traveling at more than 99.9% the speed of light, making them the fastest non-light particles that we know of. The energy is able to reach values of up to 50 joules, about the same as a baseball going 90 kilometers an hour. That might not seem that much, but remember, those are single particles, smaller than atoms. Primary cosmic rays consist to 1% of electrons and to 99% of bare atomic nuclei. Out of these atomic nuclei, about 90% are solitary protons and therefore hydrogen nuclei. 9% are alpha particles, meaning they are helium nuclei, and the last 1% are heavier nuclei. But those primary particles almost never reach the surface of a planet. Earth's atmosphere acts as some kind of shield in regard to the highly energetic primary rays. When a primary particle enters the atmosphere, it collides with an air molecule sooner or later. Upon impact into an air molecule, the impacting particle is splitted into many subatomic particles like muons, neutrons, electrons, and even antimatter particles such as positrons. By using a so-called cloud chamber, a glass box filled with supersaturated water vapor, the trails of these secondary air showers can be made visible. Neutrons generate a short but thick track in the chamber, and electrons leave a longer but narrower track. These secondary rays are what really has an impact down here on Earth. Apart from cosmic rays as in particles, space also bombards us with another type of radiation that doesn't consist of particles. Typical cosmic rays are protons and alpha particles and a few beta particles. But dying stars emit a lot of gamma rays as well, either as normal gamma radiation emissions or as gamma ray bursts, the most energetic events known in our universe. But this is only a quick side note, since gamma radiation doesn't play a huge role in what we are talking about in this video. Now that we know what cosmic rays actually are, it may be important to take a look at what cosmic rays are capable of. What are the effects of cosmic rays on computers and maybe more importantly, on ourselves? On October 7, 2008, Qantas Airlines Flight 72 was on the way from Singapore to Perth, carrying a total of 315 passengers and crew. After flying for about 3 hours at an altitude of 37,000 feet, the plane's autopilot suddenly stops working. The problem occurred literally out of nowhere, but the pilots didn't have time to tackle it. Shortly after autopilot disengagement, the flight computer alerts the pilots of a stall, but at the same time it throws out an overspeed warning, two alerts that just can't occur simultaneously. Trying to correct what is thought to be a stall, the plane automatically pitches down, letting the passengers experience 0.8 Gs in the process. The crew was able to stabilize the plane after first dive, but the entire process repeated itself again, leaving 99 people injured before the pilots were able to safely land the plane. During accident investigation, it became clear that the whole incident was triggered by an error in the ADIRU, a computer unit that feeds the flight computer with altitude and angle of attack data. The flight recorders later showed that altitude data was mislabeled as angle of attack data, leading the plane to trying to correct what was thought to be an angle of attack of 50 degrees and therefore a catastrophic stall. But for the question why this error occurred, there was no definitive answer ever found. In the end, cosmic rays may be the most likely scenario. Computers work on the basis of bits, which are assembled in bytes. A bit can either have the value of 0 or 1, depending on whether electrons are present in a semiconductor or not. Normally, that state is fixed unless we want it to change, so a 0 shouldn't just become a 1 and vice versa without us wanting it. But there is one thing that is able to mess with bit state. If a highly energetic alpha particle strikes just in the right place, it is able to flip the status of a bit. Those alpha particles mostly originate from cosmic rays. The computer is, however, able to change the status of the bit again and erase that error. That is why we call this a single event upset, or SEU, because it only happens once to a specific bit. Such a single event upset happened in the Eddy route of Qantas Airlines Flight 72 when a cosmic ray struck one of the 8 bits which label the data as the altitude information, leading it to flip. And since this single bit changed its value, the flight computer now thought the information was angle of attack data. And that effect can happen to any computer anywhere on the world, or even above the world. The higher you go and the thinner the protecting atmosphere gets, the heavier the cosmic ray bombardment gets. Single event upsets regularly happen to computers in space. During the STS-48 mission in 1991, there were a total of 161 bit flips recorded in the Space Shuttle's flight computers over a course of just 5 days. Every single one of those SEUs has the ability to disturb the code required for re-entry or orbital operations and therefore endanger the lives of the crew. To ensure the code being invulnerable to SEUs caused by cosmic rays, the code runs on 4 identical computers simultaneously. Should one of the 4 computers experience a bit flip, the other 3 computers override its information and record the exact timing and placement of the individual SEU. But for spacecraft like deep space probes or Mars rovers, carrying multiple computers isn't an option due to valuable mass being added to the spacecraft. So what rovers like the Perseverance Mars rover do is carrying a special 20-year-old computer with just 256 MB of DRAM, which is shielded and optimized to withstand higher radiation levels. But on rockets and crewed spacecraft, engineers mostly favor multiple redundant computer systems. If you want to know more about how computers are affected by cosmic rays, there's a really neat video by the science channel of Veritasium on this topic that you should watch. I can only recommend it. But not only computers have their problems dealing with cosmic rays. Your body has to endure the impact of cosmic rays all the time as well. Similar to the way cosmic rays can flip the value of a computer's bits, they can flip some bits in your body too, quite literally, by exchanging bases in your DNA, the bits of our genetic code. The DNA of basically any living being stores the information about every single cell it's made of, about every property of the individual specimen. Multiple billion base pairs encode the genes on the DNA double helix. Every gene has a different and individual function in the organism. But as we know, the genetic code isn't invariable. In fact, genetic mutations are the driving factor of evolution. If a randomly generated mutation brings the affected specimen an advantage, the mutation is likely to be preserved and given on to future organisms. Such genetic mutations normally occur randomly anywhere in the genome. There are multiple types of mutations, but all of them involve special bases in the double helix being replaced by wrong bases. That happens either naturally through mistakes in the DNA replication process or through violent events from the outside, which damage the DNA and therefore require repair. Those repair operations often insert different bases into the genome than the bases that filled these gaps before. One of these violent factors from outside the human body are, you might have guessed it, cosmic rays. Certain high-energy cosmic ray particles can, when striking the right place, destroy parts of the DNA, leading to genetic mutations. The more cosmic rays the body experiences, the more mutations are going to occur. Genetic mutations caused by cosmic rays can have positive effects, but this outcome is generally the more unlikely one. Many mutations lead to certain genes malfunctioning, false protein structures, and most commonly, the appearance of cancer. High rates of cosmic rays can pose huge health risks to the human body, which we have to counteract if we want to stay in space for longer periods of time. But apart from genetic mutations, cosmic rays have a far more recognizable impact on your body, and that has to do with the human nerve system. Many astronauts have reported of seeing bright flashes of light in their eyes during their sleep in space in the past. If a high energetic cosmic ray passes through either the retina of the human eye or the optic nerve, it inflicts a small electric current into the system. And since nerves work by passing a bioelectric signal through them, the impulse of the passing cosmic rays can be detected by the human brain. Since the affected nerve is the optic nerve, in this case, we see a short but bright flash. Knowing the dramatic effects of cosmic rays on ourselves and our machines, it may be helpful to know whether there are ways to protect people and spacecraft against cosmic rays. And thankfully, there are some possibilities. The simplest way to protect computers from radiation is just using backup computers. The same soft error just can't happen in 3 or 4 independent computer systems at the same time. For something like this to happen, you will need multiple cosmic ray particles striking the same bit in multiple systems at the same time. The probability for such an event is far less than 1 to a quintillion, basically impossible. But on some spacecraft, having multiple computer units is just impractical due to weight concerns. If your spacecraft, such as a Mars rover or other interplanetary probe, isn't able to be outfitted with multiple computers, you have to find a different solution. Luckily, most computers, which are especially endangered by cosmic rays, have some protection against soft errors built in from the start. The so-called Error Correction Code Memory, or short ECC memory, is used to detect soft errors in the system and mark the flawed bits so they can be corrected. Additional shielding with special hydrocarbon plastics can minimize the risk of soft errors occurring within the system further, since hydrogen is excellent at blocking cosmic rays and transform primary into secondary rays. Such lightweight plastics are often used to manufacture special cases for RAM and processing units to keep any high energetic primary rays from entering the system in the first place. But when it comes to crewed spaceflight missions, the protection against cosmic rays is even more essential, since we have to ensure the health of our astronauts at all times. Protecting humans is way harder than protecting computers, because the human DNA does not have any ECC memory or redundant systems like the software in a computer. Once hit and destroyed in the same place, the genetic material is changed forever. Practically, the only viable option is trying to shield the crew cabin with radiation-absorbing materials. Best for this task are, as already established, molecules that include hydrogen. One option may be using the water supplies of the crew to shield the spacecraft. When applying this method, the radiation shield would be made up of 2 walls and an empty space in between, which is being filled up with the water already required to be on board. The advantage here is that as little mass as possible is added to a total dry mass of the vehicle, and the crew is able to literally drink out of the wall. Yeah, sounds weird, but it's true. The only big problem here is the position of the water tank near the edge of a spacecraft, which leads to risk of water boiling off, a process that you may want to avoid to happen inside a fully isolated tank. Another option is using the same principle as with water, but use liquid fuels like hydrogen or methane instead. Since the tanks have to be isolated anyway, this also adds just a little bit of mass to the spacecraft, and the risk of the fuel boiling off is minimized. But as always, absorbing cosmic rays with fuel has a disadvantage. The fuel is getting consumed over the course of the mission, so your protection vanishes over time. However, the probably best option are hydrocarbon compounds, special lightweight plastics. Such materials combine low mass with high absorption potential since they include many hydrogen atoms and spread out almost evenly over the molecule. Hydrogen-rich plastics have the advantage of relatively easy handling and manufacturing, but out of all the named possibilities, they add the most mass to a vehicle, since the ability to absorb cosmic rays increases with the thickness of the material. Despite that, hydrogen-rich plastics are, at least at the moment, the best choice when looking for sufficient radiation shielding. Combining hydrocarbon shields with the water method may even be better, but not necessary. Here on Earth, we are relatively safe from the impact of cosmic rays. But in space, the picture is a whole lot different. Cosmic radiation is naturally blocked by Earth's magnetosphere and the atmosphere. But the higher you go inside the atmosphere, the less air is there to block cosmic rays. A typical airliner flying at 11 kilometers or about 37,000 feet already experiences more than 4 times the radiation we receive on the surface of a planet. And in space, outside of Earth's atmosphere, the radiation rates rise dramatically. The interplanetary space, free of any atmospheres or planetary magnetic fields, is literally bombarded with cosmic rays. The average annual doses of cosmic radiation at sea level is about 0.2 millisieverts, an amount far too small to cause any more severe damage. But on a single mass transfer, a trip taking an average of 180 days, the spacecraft and its passengers experience more than 300 millisieverts. That's over 100 times more in less time and enough to kill a human without any protection before reaching Mars. But these immense rates of cosmic rays don't stop upon reaching Mars. Since our red neighbor doesn't have a magnetic field or thick atmosphere, cosmic rays and solar particles reach the surface of Mars without being blocked by anything. Basically, the amount of radiation on the surface of Mars is much higher than on Earth. For a 500-day stay on Mars, NASA calculates a total of another 300 millisieverts, which equals a doses of 220 millisieverts a year. For health reasons, NASA doesn't allow their astronauts to receive doses higher than 1 sievert in their entire lifetime. This contingent of 1 sievert would be fulfilled by flying to Mars, staying about 550 days and going back. Not even 2 years on Mars, and the limit would be exceeded before the return journey to Earth. If we want to explore Mars and build a permanent settlement there, we really need to seek shelter. Luckily, those values are the maximum doses of radiation you could experience in space or on Mars. As soon as you have some sort of material around you, the doses decreases by a lot. We have already talked about how to protect the interior of a spacecraft against cosmic rays in Chapter 4, but how do we sufficiently shield our base on Mars? On Mars, the material used for radiation shielding can't just be a simple hydrocarbon material. For being used in the framework of a Mars base, material has to fulfill a few more criteria. It has to be structurally strong enough to support the weight of the construction and has to survive massive temperature changes. When building larger structures on Mars, it may be helpful that the chosen material is abundant on Mars so we don't have to import everything from Earth. The materials best suited for all these criteria are carbon compounds combined with multiple layers of hydrocarbons. They are very lightweight but structurally stable, are able to withstand rapid temperature changes and block cosmic rays pretty well. The only problem is the manufacturability of those compounds on Mars. Although the materials needed, mainly hydrogen or carbon, are pretty abundant on Mars, it is quite hard to isolate them and combine them into larger molecules on Mars. Carbon-reinforced hydrocarbon compounds are a realistic option when designing a Mars base, but there is another, even better option. The best natural shield against cosmic rays, apart from magnetospheres and atmospheres, are rocks and soil. Building an underground base might actually be the best option, since the thick layer of soil on top does not only block nearly all cosmic rays, it also acts as a perfect isolation and grants a constant temperature in the building. Covering the ceilings of our buildings on Mars with Martian soil is probably the by far easiest way to build a radiation shield. Additionally, the materials beneath the Martian soil only have to be strong enough to withstand the immense weight of a thick layer of soil on top and aren't required to fit all the other criteria anymore. By using special materials and Martian soil to our advantage, we may be able to cut the yearly radiation exposure of our Martian settlers down to about 1/4 or even maybe less than previous rates without sufficient shielding, enabling longer stays without gigantic health risks. Oddly enough, SpaceX plans to not equip Starship with additional radiation shielding at all, meaning the radiation doses is way higher. Despite that, the stainless steel hull of Starship offers some minimal protection. According to Elon Musk, that little bit of metal should be enough to ensure the crew's safety. I highly doubt that, especially during solar storms, but we will see how it turns out. Cosmic rays are a threat that is underestimated far too often. Despite only being single particles, they can cause a lot of damage to our technologies and ourselves. It is of high priority to find some sort of protection. The impact of cosmic radiation is probably the limiting factor for long-term Mars missions or ISS expeditions. Our bodies are just not built for these insane amounts of radiation. The further we go, the more we have to learn about the dangers of space and how to survive them. If we want to expand, we need to find ways to protect ourselves from all the death traps the universe has set up for us. Our technology, in terms of radiation protection, is still far too insufficient for trying longer interplanetary missions. Limited by mass constraints, our current solutions are just too heavy to grant the safety our astronauts need. And that's already it for the deep dive on cosmic rays. What do you think? Will future spacecraft finally receive some sort of radiation shield, and what will it look like? Let me know in the comments, and if you enjoyed the video, which I really hope you did, why don't you hit the like button and subscribe to the Rocket Shop? I really appreciate all of your support. We see ourselves in the next video, and until then, I'm out. Cheers!